Can we start? Hello?
Hello?
Hello, student volunteer. Can we start now?
YouTube has started.
Okay, thank you. So welcome to day 3 or day 2 of the technical program of ISMA 2021. So here is the 7th session, modeling. So I'm Shohei Mori at Graz University of Technology. So in this session, we will have 5 presentations, 1 from journal track and 4 from conference track. And actually, we are missing 1 presenter, the second presenters of the author. And so please join us as soon as you can. And so we are strongly connected to the social media services, so like Twitter, for example. So if you want to share your experiences at ISMA, don't forget to put the hashtag ISMA21. And also we have Discord channels. And if you are the attendees of the ISMA, and then you can find our session groups or something, namely in the paper session 7 modeling. So you can have the questions here, in the Discord or in the Zoom chat. Please don't hesitate to post any kinds of questions that all would be helpful to all the authors. And after the session, so each session will, each presenter will have about 12 minutes plus the Q&As. But if you don't feel comfortable about this, so you can just go to the gather together system, and you can directly ask to the authors after the session. So now we can start. And so let me introduce the first presenter. So Han-Jin Yang is an associate research director in SenseTime Group Ltd, China. His research interests focus on computer vision, including video enhancement, multi-view stereo, 3D reconstruction, and augmented reality. So please, floor is yours. So please go ahead with the presentation.
Thank you, Jack. Let me share the screen. Hello, everyone. Today I will present our work titled Mobile 3D Scanner, an online 3D scanner for high-quality object reconstruction with a mobile device. As we know, 3D object scanning is one of the core technologies of digital content creation in a wide range of graphics and AR applications. And for these applications, the reconstruction quality of 3D object models is of primary concern. Existing real-time static object reconstruction system can be divided into 2 categories. One is a RGBD-based 3D scanning system, such as Kinect Fusion, Infinite 10, Bundle Fusion, which takes RGBD frames as input and checks the camera pose by ICP. The other is the image-based multi-view reconstruction system, which checks the camera pose by SLAM and estimates depth by MVS. The depths are fused into a global model by TSDF or Surface. Monofusion and mobile fusion are typical works of this category. However, most systems are more suitable for PC due to time complexity and are limited in reconstruction scale due to the limited memory resources of mobile devices. Besides, the geometric details of the reconstructed models by these methods are greatly influenced by the depth errors or over smoothness of consumer depth sensors. So we present a new 3D scanning system for high-quality online object reconstruction on a mobile device, which we name as a mobile 3D scanner. Unlike most existing 3D scanning systems on mobile platform, which can only scan small objects, our system can reconstruct objects with larger dimensions, such as status and static humans. We propose a novel visual inertial pose tracking method for accurate real-time object tracking with a mobile device. An adaptive TSDF voxel resizing strategy is also proposed to solve the memory limitation during TSDF. Besides, we propose to refine the depth from the embedded sensor by a multi-view SGM approach and an efficient shape-on shading method to further improve the geometric details of the object model online. Here's the workflow of our mobile 3D scanner system. As the user scans the object by a mobile device with a rear RGBD camera, our pipeline tracks the 6-stop process of the object in real time using visual inertial ICP on the front end, while maintaining a keyframe pool on the back end with a local BA and a loop closing module to refine poses of all the keyframes. Simultaneously, the incoming depths are fused to a TSDF model with adaptive voxel resizing for real-time preview. When the user finishes scanning, an object model post-processing module is activated, in which the keyframe poses are optimized in a global BA, and the object depths of each keyframes are optimized by SGM. The optimized keyframe depths are fused by the globally optimized poses to a final TSDF model, followed by matching cubes, post-on surface reconstruction, and SFS to get the final 3D mesh. Finally, the 3D mesh model is mapped with multi-view images to get the final texture mapped 3D model object. In the real-time scanning process, our system localized the camera pose by loosely coupled integration of ICP and MU in a real-time tracking thread on the front end, which predicts a pure pose by MU estimation and integrated into ICP tracking. Meanwhile, we optimize our sliding window of the keyframe in a local mapping thread and perform loop closing in another thread on the backend for further optimization of the track poses. The original ICP solution of Open3D is sensitive to depth errors or over smoothness. To better solve these problems, we add a reliable rotation and gravity constraints as our new ICP energy terms. Meanwhile, a local mapping module is necessary to further reduce accumulated errors by local post optimization, with a loop closing model for global post optimization on the backend. We improve the local BA by using keyframe depths as constraints, as can be seen in the camera trajectory and the fused 3D models. The tracking errors are significantly reduced by loosely coupled integration of ICP and MU, while local BA with depth constraints and loop closure further improve the accuracy of keyframe processing significantly. Meanwhile, the depth inside the object region of each keyframes are fused by its tracked 6-stop poses into a global TSDF model in another fusion thread on the backend. TSDF fusion is memory consuming on a mobile device, although using voxel hashing. To better overcome this issue, we propose an adaptive voxel resizing strategy, which sets up a limitation of memory and dynamically enlarge the voxel size to avoid out of memory, with new TSDF calculated by trilinear interpolation of the old ones. With this adaptive voxel resolution, users are able to use a mobile device with limited memory to scan as large as possible objects. Actually, the voxel resizing is triggered iteratively whenever the memory limitation is reached, until the object scanning is completed. After the user finishes scanning, a post-processing module is activated in which keyframe depths are fused to a final TSDF model. Directly using the local optimized pose and the input depth for 3D model fusion is insufficient for a high-quality reconstruction purpose. Because the input depths from consumer RGBD cameras such as P2f on iPad Pro might have depth errors or over smoothness with lost geometric details. To solve this problem, The keyframe poses are optimized in a global BA. With globally optimized poses, we propose to estimate more accurate depths with geometric details for all the keyframes by MBS. We improved the multi-view SGM approach by incorporating DTOF depth appearance into the cost aggregation to exploit the complementary advantage of MBS and DTOF. As can be seen, the object depth refined by our SGM with DTOF depth pairs contain more geometric detail than the DTOF depths and are more complete in textureless regions. With the optimized keyframe poses and depths, a final TSD fusion is performed for better geometric accuracy than the real-time preview one, using a similar adaptive voxel resizing strategy at the scanning stage, followed by matching cubes to extract the mesh of the object, and person surface reconstruction to deal with the incomplete mesh problem. Then we use shape-on shading method to improve geometric details from the shading clues. Although SFS is helpful for detail restoration, most existing implementations, such as intrinsic 3D, take several minutes on PC. Instead, we propose a highly efficient SFS implementation for detail enhancement on mobile platform, which takes only a few seconds on iPad Pro. For time efficiency on a mobile device, we perform SFS directly on the mesh by optimizing an intermediate triangle normal map, followed by updating the vertical positions according to the optimization of the normal map. For SFS optimization, we follow the cost-defined pyramid strategy with mesh triangles upsampled by loop division. We assume that scene is Lambertian and parameterize the lightning with spherical harmonic space functions. The 3D model refined by SFS is finally texture mapped using the color images of all the keyframes with globally optimized poses. Here we use our mobile 3D scanner to successfully reconstruct several static objects on iPad Pro, including normal size movable objects, large movable objects, and very large immovable objects. These experimental cases are performed on iPad Pro 2020 with the core algorithms implemented in C++. We qualitatively and quantitatively compare our mobile 3D scanner to other state-of-the-art methods on the experimental cases. Our system performed better than other works in the finally generated 3D models with better geometric structures and fewer noisy artifacts. We can also see from the model accuracy evaluation in the table that our mobile 3D scanner reconstructs the object models with a millimeter level accuracy, which turned out to be the best in both RMSE and MAE. We can also see from the time statics tables of our pipeline on three typical cases with size varying from a normal size movable, large movable, and two very large immovable objects. We can see that the larger objects will cost more time on post-tracking and TSD fusion, and larger objects with more keyframes takes more time on post-processing. But even for the largest case on worker in the table with the most keyframes, our mobile 3D scanner can still achieve real-time scanning and efficient post-processing for online 3D reconstruction on a mobile device. And that's our presentation for this work. Thank you.
Thank you, presenter. So now we are moving on to the Q&A. Does anybody have questions from the floor? From the audience, sorry. So let me check the chat and the Q&As. Please don't hesitate to join us. So yeah. Meanwhile, maybe I can have some questions. So I think the recent progresses in the mobile devices quite amount, and then so the desktop hardware and the mobile devices are getting more closer and closer in terms of the performance, for example. And even for the mobile devices, we have more sensors, which is basically beneficial to the SLAM system or the modeling system or scanning system. So being said, so what is the most advances or the specific part that can design for especially for the mobile devices in your case?
You mean that what strategy can be designed for mobile device, right? I think the most important is time efficiency and memory. These are two main concerns when we are developing a system for mobile device. So for take an example of our system in this work, we try to use strategies such as adaptive TF voxel resizing to avoid out of memory, and we try to optimize the linear equation solving and some other process that takes too much time on PC, to let it run very quickly on mobile devices. I think that's the two main concerns when we are developing a mobile system.
Okay, thank you. Maybe I have additional question regarding that. So I think the resizing, regarding the resizing, how often do you see the resizing in your real environment tests?
For the small object, the resizing usually do not happen. But when we scan status outside, just status which are taller than a human, then maybe the resizing may take 2 to 3 times.
Okay, thank you. Okay, so we have some questions from the audience. So from Giba Soros, if I'm pronouncing him correctly, he said, is this purely on CPU or is it using the mobile GPU too?
Some of its part is on GPU. For example, some processes such as silicon shading, TSDF fusion, it takes GPU, and for other parts, it's on CPU.
Okay. Yeah. I think that was the answer. And so I have another question from Costas. He said, a very interesting work, thank you. And is the application available somewhere to test? So is there maybe the code available?
Currently not available, but we are planning to give a executable system, maybe on a PC version in future for other people to test it, experiment on it, using the data, the data format that we define. Yeah, we're planning to do that on the and we will share it in a home page, is in the website of our paper. Yeah.
You mean the project page somebody posted in the on Discord channel, maybe? I mean, your co-author have already announced the web page. Okay, so maybe this would be the last question. So from Gaber again, he says, what is the latest, largest thing you have tried to scan?
The largest thing I think is a line. It's a line in the teaser of our paper. It's a largest thing. It's more than two meters wide, and another line, Asian line in a also in the experimental cases of our paper. It's more than 2 meters tall, and it's maybe the largest we have tried.
Okay, thank you. So I think we are running out of time. So let's move on to the next presentation. So please, yeah, thank you for your presentation.
Stop.
Yeah. So welcome, Kankan. We are happy to have you here. Could you start sharing your screen because we haven't tested it yet? But
okay,
meanwhile, I can introduce his PO here. So Kang-won is an associate professor in the School of Computer Science and Engineering of Nanjing University of Science and Technology. His research interests include human body modeling, 3D reconstruction, non-rigid reconstruction, and motion tracking, augmented reality, and virtual reality. Quite diverse. That's good. And and then I have an additional announcement to the audience. So we will have a Q&A track in a room of Gather Town. And you can also find the room by following one of the student volunteers. So he will soon announce how to do this. So if you don't feel comfortable about questioning here, you can also join that session late after this session. Okay, so floor is yours. Please, Kang, start your presentation.
Thanks. Hi everyone, my name is Kang Wang. I'm so glad to have the opportunity to give a report in the conference. Our paper title is Parametric Model Estimation for 3D Closed Humans from Point Clouds. I present our paper in the 5 aspects. First, let me briefly introduce the background. In recent years, many applications in virtual reality and augmented reality has been arising. For example, the Google Starlight, Microsoft Holoportation, and virtual dressing. A major technique behind these applications is 3D human shape estimation. The goal of 3D human shape estimation is to accurately recover a full detailed 3D image of a human body. With the development of depth cameras, the capture of point clouds becomes easier. Due to the large variations of human pose and shapes and clothing details, 3D human shape estimation from point cloud is challenging. In addition, self-occlusions of human bodies and no color image information makes this problem more difficult. Recently, many 3D human shape estimation methods have been proposed. Some works predict the parameters of a statistical body shape model directly. The reconstructed shapes do not contain surface details, such as clothes. The recent work, the reference term can recover the non-parametric shapes of closed bodies. However, the lack of semantic information in the non-parametric representations limits their applications like body reposing and garment retargeting. The reference 4 recover the parametric models using the optimization-based registration, but the performance highly relies on the accuracy of predicted correspondences. In this paper, we proposed a hierarchical regression approach to predict the parametric models for 3D closed humans from partial point clouds. In our framework, 3 regression networks are cascaded to regress 3D model parameters from cos to phi. In each stage, we first extract global features, local features, or vertical level features, the point clouds, and then estimate and update to the model parameters through a regression network. We decompose the closed human body into the undressed body and the clothing detail. The undressed body is a model with a well-known model, the SMP model. And we reprint the clothing detail using an offset, an actual offset on the SMP model. So from a set of SMP model parameters and the clothing offset, we can obtain the detailed homosapes with the SMP model framework. The first network of our method, the global regression network, estimates a rough undressed model based on the global deep feature of point clouds. We adopt PointNet++ to extract global deep feature on the point cloud. Then we employed a fully connected network to learn the parameter of the undressed mass. The objective function consists of the 3D correspondence loss, the parameter correspondence loss, and the adversary loss. The 3D correspondence loss arrives the predict mass to the ground truth mass, and the parameter loss makes the estimated parameter to be close to the ground truth parameter. And the adverse loss can prevent the network from generating 3D model with unreasonable body shape and poses. The second network, the local regression network, aims to refine the undressed model. In the global regression network, the global features ignore the local structural information of the human body. So the local structure of the 3D model cannot be fully recovered from the global features. The global regression network utilizes the local deep feature of human joints to refine the undressed model. For each joint on the initial model, we search the neighborhood by finding the neighbor points from the input points with a radius around the joint. Then we extract local features with a shared mini PointNet for all neighbors. The local features of all joints are concatenated to form a single feature vector. Finally, we use or fully connected network to regress the parameter update from the local future vector. In the vertex level regression network, we aim to recover the closing details by inferring the per vertex displacement. Based on the undressed model, the neighboring paths of vertex can be extracted on the point cloud by searching the neighboring points within a radius. The points in the paths are then encoded with a mini point net to generate vertical level features. The points in the paths are then encoded with a mini point net to generate the vertex level features. The features of all vertex are then concatenated. From the vertical level features, we adopt a hierarchical graph CNN to infer the detail offsets. The portrayed model on synthetic datasets does not perform well on real data due to the domain gap. For example, there is a large difference between the predictor mass and the input point clouds. To address this problem, we built the correspondence between the input point clouds and the initially predicted mass, and use these corresponding points as the CO2 cloud truth correspondence to fine-tune our network. With the built correspondence, we can formulate the self-supervised loss of regressing the undressed model and the closing details. In this example, we can see the undressed model after the fine-tuning becomes more consistent with point clouds in both human pose and shape, and the recovered detailed model fits to the point clouds accurately. To demonstrate the effectiveness of our method, we first compare our method with state-of-the-art methods for human shape estimation from point clouds. The comparing results demonstrate that our method outperforms state-of-the-art method in recovering detailed 3D body models from point clouds. Our method not only regresses the parametric model, but also recovers the 3D closed humans. We also compare our method to three kinds of three kinds of model fitting methods. These model fitting methods can work well for the data with relatively small poses. However, the error is large when tested on sample with strong occlusion or large poses. The model fitting methods highly rely on the accuracy of joints or correspondences. In contrast, by learning from sufficient training samples, our method can achieve much higher reconstruction accuracy. We test our method on real data captured by a Kinect. The input is the sampled point clouds on the depth. Our method can robustly and accurately estimate 3D shape and pose and closing details. Our method's applications, and we saw two application scale. The first one is the body reposing. The parametric representation allows us to edit the detailed human shape conveniently. For example, generating the clothed bodies with new poses. In addition, the detailed human models can be integrated into a real scene for AI applications. This AI example can give rise to many practical applications in certain circumstances. For example, AR showing in the museum, entertainment effects in online games, and so on. Finally, I make a simple conclusion of the presentations. In this paper, we present a novel hierarchical regression framework to estimate the parametric model for 3D closed humans from point clouds. We design a scheme of exploiting different discriminative features from point clouds. Our method is also generalized successfully to real data. In the future, we can further enhance the high frequency details on the models and recover the details of loose clothes, such as skirts. We also plan to reconstruct the parametric and detailed 3D human motions on sequential data. Thank you.
Thank you for the nice talk, Kankan. So let's move on to the QA session. So far I don't see any questions in the chat in all the systems, so maybe I can start. So if I understand your method correctly, I think so what the system does is to firstly capture the single frame of the from the RGBD or the range sensor, and then so that the system can fit a base model to that scanned person. Is that correct?
Yes.
Okay.
The input to our method is the point clouds. The point cloud is generated from a single depth frame. From the point clouds, we directly predict the human shape, including the undressed body and the clothing details.
Okay, cool. And so then my next question would be, so I think your method doesn't target into extracting any colors out of the RGBD sensors, for example. And so do you have any specific applications in mind? You know, for augmented reality over the virtual reality, I think it's important to capture the colors as well to get the details of the person or the captured person here.
I think this is a good future work by combining the color information with the depth information. In the beginning, we aim to devise a framework only from the depth information, because in some circumstances we only obtain the depth information, and also the depth camera cannot get good color information from under some circumstances. For example, under the sunlight. So only the depth information is available.
Okay.
I think with the information of color images, the details of the human body can be recovered better.
Okay, thank you for the answer. And so we have one question from the audience. So from Mattia Colombo. So awesome work. Does the complexity or the level of details of the input mesh influence the computational requirements for the system?
the computing our method are not the level of the detail of the on the input mask do not have the do not affect the computation requirements for our system, because our system is trained beforehand. The inference time is very fast.
Mhm.
We can the reported time on our general GPU card, our time is close to real time. Because our framework consists of 3 stages, so the total time is a little less. About the time is about 50 seconds. I think the complexity and the level of the details do not influence the computations.
Okay, thanks for the answer. I think, yeah, the answer was great. And so let's thank to the authors again, and let's move on to the next presentation. Thank you, Kankan.
Oh, thank you. Thank you.
So please be prepared, Shan Xiao Li. Yes, sorry, Ji Hao Li.
Yeah, sure.
Okay, so
sure, and I will share my screen.
Yeah, thank you. Meanwhile, I would like to introduce you the authors. So Ji Hao Liu is a master student at Shenzhen Institute of Advanced Technology Chinese Academy of Sciences. His research interests include virtual reality and computer graphics. So I think I have forgotten to announce all the papers titles till now. So let me do that from now. So he's presenting building sketch, freehand mid-air sketching for building modeling. So floor is yours, please go ahead.
Yeah, sure, thank you. And I'm going to start. Hello, I'm Ji Hao Liu, currently working at the Tencent game. I'm going to present the building sketch, a novel media sketching system for modeling 3D structured buildings. Buildings are the most common man-made objects in the real world. And however, creating 3D buildings using the common CAD software is a very expensive process due to their complex structures. Recently, a number of methods for modeling buildings have been proposed. For example, the procedural generation can use a set of generative rules to produce 3D buildings automatically. However, this method requires a programming and architecture knowledge and are difficult for users to directly control the 3D shapes. By contrast, the interactive modeling is a more intuitive way to freely create 3D objects. But previous methods are generally based on 2D sketches, which is hard for 3D control. And more recently, several VR-based modeling systems were also proposed, but they generally ask the users to draw the whole surfaces by using a number of ribbons. To create 3D buildings using this method would be still tedious. Our goal is to design a novel sketch-based modeling system for modeling 3D buildings. It should be intuitive and easy to use, with flexible control of the overall building shapes. Also, the instantaneous feedback is essential for providing a fluent user experience, especially for the artists during the conceptual design stage. In our work with the aid of the recent VR devices like Hermes and Reconstruction, we designed a hybrid system for modeling 3D buildings that integrates the powers of the freehand 3D sketching with the deep learning and the automated procedural generation technologies. Concretely, the user first draws a few 3D keystrokes in midair to outline the desired building shapes, and then a neural network is used to predict the most possible types from the strokes. For this example, it is identified as a cube shape. And finally, we use a grammar-based generation algorithm to produce a detailed mesh model automatically. Here's a demo video. The user first draw a freeform building mass and adjust its appearance through the control panel. Then create a cuboid building mass. And next, create a hip roof on the top of the building. And a building with tilted facade. As you can see, our system enables users to generate 3D buildings progressively by drawing very few 3D keystrokes. Yeah, okay. Next is the algorithm implementation. First, our system supports a set of predefined object types, including 3 types of building masses, that is the cuboid, cylinder, and freeform shapes, which are the main body of the buildings, and supports 6 kinds of roofs, like the hip, round, cone, and pyramid shapes. Also, the users can allow to sketch the stairs outside. Then to interpret the user-drawn shapes, we designed a recognition network to predict the object types from the 3D strokes. The network uses a LSTM module to process the input strokes with variable number of points. The output is a vector indicating the scores of n categories. The one with the highest score will be considered as the best matching object type. As a result, on the test set, we finally obtained around 97% accuracy. After recognizing the object types, our method will automatically synthesize the detailed 3D geometry that can match the stroke shapes well. For the cuboid and the cylinder shape building masses, we adopt the rotating calipers method and the least squared algorithm to fit the rectangle and ellipse shapes respectively. And our system also allows the users to design freeform building masses by sketching irregular top strokes. And here we use another neural network to classify the stroke points into 3 categories. That is the corners, the curve points, and the line points. And concretely, we adopt the PointNet, which is a highly effective network for point size segmentation tasks. And after the segmentation, we can easily produce straight and curve-shaped facades by the line fitting and the cubic Kermit splines, respectively. Here are some stroke segmentation results and the corresponding building models. And as a result, on the test site, we finally obtain about 95% accuracy. The users can also optionally draw several downward strokes to specify the facades. The downward strokes can be used to adjust the building height, the inclination angle, and also the user can use multiple strokes to depict the shapes of the different facades. And moreover, this operation can also work for the cylinder and freeform building masses. Afterwards, the floors, windows, and other ornaments will be automatically generated based on previous procedural modeling method, which uses a collection of simple grammars to describe the facade details. And furthermore, our user interfaces also provided options to adjust the building appearance and the procedural parameters, such as the wall texture, window type, and floor height, etc. For creating the staircases, we use the wave stroke to represent the stairs and only enable the users to create them closing attached to the facade. And the wave shape of the stroke only indicates its type, and the actual number of turns is the same as the floor number of the attached facade. As for the roofs, we only need to extract some basic geometrical information from the 3D strokes. For example, the roof height and the necessary stroke endpoints. With this information, it is very easy to form the corresponding roof meshes. Moreover, the free drawing of strokes can also help to produce more roof variations. These examples are extended from the dome, hip, and the pyramid roofs, respectively. Also, the users can assemble multiple roofs together to form more complex structures. Moreover, to better combine multiple parts and support snapping operation, we describe the building structure using the hierarchical trees. And here is an example video of snapping operation. Yeah, okay. Next is our results. And here are several 3D building models created by our system. These models have various shape features like the freeform building masses, tilted facades, free combination, and the stairs outside. We also try to reproduce a set of buildings by using real photographs. The second column shows the artistic modern buildings with highly unusual shapes, which are hard for traditional methods to create. However, through our system, users can create these shapes very easily and intuitively. Then we compare our method with the previous 2D sketch-based method. First, they use the 2D sketching, which suffers from predicting possible 3D depths, and they only produce the template buildings with regular shapes. For these two examples, the user tries to create the curved facades. However, the resulting models are the straight plans. Also, the users have to sketch almost all the edges to depict the shapes. By contrast, our system can successfully produce such kinds of freeform shapes, and we just require much fewer strokes to outline the building shapes. For the user evaluation, we performed two simple experiments. In the first task, we invited 10 participants to experience our system by freely create 3D buildings as they want. Here are some example buildings created by the participants. We then asked them to rate our system on 10 questions using the SUS questionnaire. According to the statistical results, we can say that the participants think our system is easy to use and easy to learn. And also, the functions in this system were well integrated. And in the second experiment, we asked the user to reconstruct a very simple building according to a given image. As a result, we can see that all participants successfully created buildings similar to the target shapes visually. And here we mark each building block with different colors so as to see clearly how the user decompose the building structure. And we can see that the people usually take different ways to observe the target building, which also demonstrates the flexibility of our system. And in summary, we propose a novel freehand sketching interface to design 3D buildings by combining rough 3D sketching and deep learning to enable the users to just focus on the overall building shape design. And certainly, our method also bears limitations. For example, our current implementation uses too many buttons to adjust the appearance, so that limited choices of the appearance styles are provided. Therefore, a more expressive user interface for appearance control is still necessary. And that's all. Thanks for listening to this talk.
Thank you, Xinhao. It was really nice talk and nice work. And so let's move on to the question section. And I think, okay, I have one question in Discord. So from Luis Lawrence, do you have a link to the project? It looks cool, and very cool, excellent presentation.
Yeah, sure. And we're about to release the course maybe around this month, maybe. Yeah.
Okay.
And yeah.
Cool. So we have now no questions in the other system. So let me ask some questions from me. I think in some of the beginning of the slides, I think I saw some design choices about the categories of the, for example, the roof shape or roof shape, or the shapes of the building itself. And then, so did you have something that you needed to discard as a categories of those? Like, for example, this category is just too complex to be implemented in this system, or otherwise something that is not really useful for the users, or something like that?
Actually, I think all these provided categories are very common in the real buildings, and especially for the cuboid building masses and the second building masses, and they are very common in the real world. And for the roofs, and actually we have just searched the most common roof types in the internet, and especially for some papers related to the architectures. And we find that all these types are very common for the building design, so we chose these types. Yeah.
Okay, thank you. And so But actually, when you say the common building design, it's about the European types of buildings, I suppose. So do you have?
Yeah, sure.
Do you think your system is scalable to the other, types of buildings, like in buildings in Asian, for example?
Yeah, sure. And as you can see that for the windows and the doors, and we're just using some Western styles. And if we just collect maybe some like Chinese or Japanese styles prefabs, and we can just attach them into the building, so we can produce maybe like the Eastern style buildings. Yeah.
Yeah. Okay. So I think we have a question from the floor, from the audience. So from Stephanie Zolman. Thanks for the interesting presentation. How well would the system work for different types of buildings? How flexible it is? Is it to retrain? So I think it's somehow related to my previous question, but yeah.
Yeah, sure. And generally for our system and our network could predict the accurate types from the strokes. But yeah, certainly sometimes our network might produce some wrong prediction. And for example, for the 3 building bodies, that is the cuboid, secondary, and freeform building parts. And even if they are predicted wrong, for example, the strokes are originally the roofs, it can still generate the corresponding meshes from the for the building bodies, since our system can take no matter one or more strokes as input. And but for the roofs, since we mainly extract the stroke endpoints from the input, if no sufficient number of the endpoints are detected by the system, and we will just discard the drawing this time. And certainly, if the system generates wrong meshes, and the users can just decided to withdraw the latest operation and then draw a new one.
Okay, thank you. I assume you answered the question. So, okay, we have another question from the audience, from Mattia Colombo again. So, very cool work. Do you think it would be possible to have the user add some simplistic features to the input drawing, for example, an ornament or colors that would be reflected in the output?
Yeah, sure. And in the future, and we could add these functions. And at the moment, and our system can only support the user to change the window, the forehead, or the window or doors density, or just some textures, or maybe some predefined models. And in the future, and we can add these functions to provide more choices to control their appearance. Yeah.
Thanks. I think we still okay. That's all from the audience. So let's thank the audience again. And let's move on to the, thank you. Let's move on to the next presentation. Okay, so hi Lee, could you share your screen? And meanwhile, I would like to introduce you to the audience. So Heidi is a PhD student at Young University. His research interests include visual localization, SLAM, and 3D reconstruction. So the paper title is BD-Loc, Global Localization from 2.5D Building Map. So please go ahead, highlight.
Hello, everyone. I'm Hai Li from Zhejiang University. In this work, we propose BD-Loc, a hierarchical global localization framework based on the 2.5D building map. 2.5D building map is a special 3D map that illustrates the rough shape of buildings, which has been integrated into some mapping services like a Google Map and OpenStreetMap for many years. This kind of map is constructed by top-view building controls with height measured by remote sensors. This process can be executed either manually or automatically from satellite maps and the digital elevation models. Compared to the dense 3D map that includes a great number of faces with complex textures, the 2.5D map is composed of several textureless faces close to the building periphery, saving massive storage memories and the transmission bandwidth. However, the simplicity brings a considerable loss of details, which make the 2.5D based localization task challenging. In this work, our goal is to find the 6-DOF pose of a given street view image with a 2.5D building map obtained via the coarse GPS signal. The red mask is a reprojection of the 2.5D buildings using the estimated pose. Most 6-DOF visual localization approach employ the feature matching-based strategy by finding correspondences between 2D key points extracted from the street view image and the 3D dense point cloud. These methods require the reconstructed dense texture models. The previous 2.5D based localization exploits the line segment correspondences, which require fixed height and approximate orientation, which limits the view freedom and degenerates the problem to a 3-DOF pose refinement. Since the 2.5D has no texture information and doesn't accurately match the shape with actual buildings, the cross-view geometry correspondence are unstable. The proposed BD-log framework consists of 3 phases. The lifting phase, which is the gray part, predict the semantic map and the depth map from the current image and extract the building segments for further refinement. Then back projected to 3D and get view building points. The registration phase, the green part, first download the surrounding 2.5D building map, use GPS signal and sample view depth points from the current position. These 2-point sets are fed into a feature extraction network followed by a coarse pose estimation via matching-based alignment. Finally, the optimization phase, which is the yellow part, iteratively optimize the pose supervised by the occupancy distance of building silhouette and the rendered silhouette. The primary purpose of the lifting phase is to unify the representation between the image and the map. We take a simple unit architecture to predict semantic segmentation and the depth map from a query image. Notice that this phase can be replaced by any other state-of-art methods for better performance. The goal of the registration phase is to find the point correspondences for predicted depth points generated in a lifting phase to the surrounding 2.5D map. However, compared to the scanned point clouds, the points sampled from 2.5D maps are excessively uneven, which is too dense near the building surface and thoroughly empty for the other space. Moreover, the rough building shape cannot maintain the uniqueness of the local geometry feature, which further degenerates the feature distinctiveness. To improve the feature extraction ability for this task, we propose sparse point graph architecture named SPGNet, which is a hybrid point-wise feature extraction network that encodes both local geometry and global relations. Our SPGNet adopts a 2-step U-shaped structure to compute the point-wise features. The sparse voxel-based convolution layers are leveraged to encode the local geometry features. After that, we apply the graph convolution based on the undirected view graph constructed on the output coordinates of sparse 3D convolution. The graph convolution aggregation and updates features spatially based on a message passing paradigm. The view-dependent graph selected the depth interval by projecting the points to a cylinder surface centered at the origin of the local coordinates. The edges are generated from the projecting node using the k-nearest neighbor algorithm based on the surface distance. The cost pose solved from a registration phase are not optimal. Therefore, we propose a refinement method which leverages the differentiable silhouette rendering method to maximize the building overlap. We propose a mask optimizer based on soft rasterizer. The mask is used to block the gradient from the invalid area, which could interfere with the optimization directions. In this case, we only consider the boundaries between the sky and the roof. You can see from the optimization phase, the middle is the output from the registration phase. And after the optimization, we got the final red mask. We compare the feature matching recall and the localization accuracy on three data set. Due to the reconstruction noise and the inaccurate 2.5D building map, the performance on the real-world data is not as good as that on the synthetic data, even though our methods still outperform the others by a large margin. The image shows the optimization process from the top to bottom are the AR result of the initial pose, optimize the pose after 10 iterations, 50 iterations, and the final pose. We can loosely couple our localization method with SLAM to perform outdoor augmentation reality, which predict the global transmission. We can show the virtual object placed in desired position in the world coordinate system. Okay, that's all. Thank you.
Thank you for the nice presentation, Hailey. So let's move on to the Q&A. And so far, I don't see any questions, I think. Let me check. No. So yeah, while waiting for the questions from the audience, I would start some. So I think I've read when I've read your paper, I think the paper says you are not using the compass information, which means the rotations of the initial pose, I think. Is that correct?
So sorry, please.
Do you use the compass data? I mean, in addition to the
No. I only use the cost GPS signal. No compass.
Do you have any so my simple question is why not? Why don't you use the compass information? Because it sounds useful and always accessible, especially for the mobile devices.
So our motivation is to minimize the prior informations. And the compass, so previous methods use compass to limit the initial orientation. But in some urban scenarios, the compass may be not accurate enough. Well, so when the initial compass is biased too much from the accurate orientation, the method is totally failed. So GPS can give you quite accurate initial positions, and the noise is controllable, and so we don't use the extra compass signals.
Okay, when you refer to the previous work, I think which means the Kremen's work, I mean Kremen's artworks and his colleagues, and then so like the edge-based 2.5D registration.
Yeah.
And then
Yes.
I think it was presented like 5 or more years back, and then I guess there are some improvements in the compass estimation or the orientation estimations, but still you think it's not that much useful for your system or the registration using 2.5D maps.
So for practical usage, I think compass is useful, but in our research, we want to limit. Don't use too much prior information, so we don't use a compass in this work. So yes. Okay,
thank you. So we have one question from the audience from Gabriel Soros. Are the camera frames processed independently? So I think, do you have any consistency in time between the frames or something?
Currently in this work, the camera frames process. Yes, the first stage is independent from the second stage. Yes, and so the framework is replaceable, and we can replace the depth estimation and the semantic segmentation methods for better performance. Yes.
Okay, assume you answered the question. Okay, we have another question from the audience, from Stephanie Solomon. For the real data set, how many images did you capture? What is the minimum amount so that it works well?
We for the real data set, we use the 3D reconstruction to reconstruct the whole. It's like a park. It's about kilometers long, and so the range is about 1 kilometers plus multiply 1 kilometers range, and the real world 2.5D map is not so well, so we have to manually modify the 2.5D buildings to with our reconstructed 3D model, and it's I don't get it. What is the minimum amount so that it works well? So it's about 10,000 images.
10,000 images.
I think totally. Yeah.
For the real data set, right? Not the synthetic one. Maybe some of the details are already in the paper, I guess. But
you can read the paper.
Okay, thank you.
If some further questions.
So, any questions from the audience? No, maybe I can have another question. So I'm curious about the speed of the inference. How fast it is?
We haven't detailedly computed the speed. I think it's about 1 second per image, such like that. But since our application is not real time, so we use it to loosely coupled with some SLAM systems, so it doesn't really matter about time. Yes.
Okay. And I think from the video, when I watched the video, I think some errors on existing about the along the floor level, like it's just jumping a little bit towards up and down, I suppose. So what would be the reason for this?
So we use the SLAM for the we SLAM to calculate the real time pulse, and when the 2.5D localization works and produce our pulse, we calculate the transformations between the current pulse and the global pulse. The jiggle may be caused by this transformation calculation something, but I think it's quite stable. Mm-hmm. So after the transformation.
Okay, thank you. So thanks again to the presenter, Hailey. Thank you. And let's move on to the final presentation, the 5th presentation. So Min, could you please be prepared for the slides? Okay, so meanwhile, I would like to introduce her to the audience. So Min is a PhD student at State Key Laboratory of Virtual Reality Technology and Systems at Beihang University. Her research interests include augmented reality, virtual reality, and 3D reconstruction. So, floor is yours. Please go ahead, Min.
Oh, okay. Hello, everyone. I am Meng Ming from Beihang University. Today, I will introduce our work, distortion of real room layout estimation from a single feature image. I will introduce this work from the 4 parts. First, I will give a brief motivation. Then I will introduce the repeated work. Next, in the overview of our method. And finally, I will show some experiments and results. Now let's start. The input to our method is a fisheye image captured by single lens using non-linear projection. It has the advantage of large fold. It provides the entire visual content around the cameras for layout estimation, giving rise to more sophisticated scene understanding and reasoning, and bring broad application prospects for VR, AR, and MR. The study of layout estimation using the fisheye image as input in the method on the right, which combines the fisheye camera with the depth camera, but the utility is poor and the cost is high. LayoutNet utilize panoramical image and deep neural network to capture the structural layout of the room, not making use of geometrical information. It is difficult to handle complex scenes with severe objection, occlusions, and clutters. HorizonNet leverages INs in layout estimation task to learn the long-range geometrical pattern of room layouts for improving the accuracy. CFL introduced a convolution defined in equirectangular projection to compensate for the distortion of panorama. However, these layout estimation methods cannot perform well on fisheye images, mainly due to lack of public fisheye dataset as well as significant distortion. The overview of our work is shown in the figure. We introduce an encoder-decoder strategy for the layout estimation from a single fisheye image. The fish map is extracted by ResNet 50 with distortion-aware model in encoder. In decoder, we exploit bidirectional LSTM with two-dimensional step model for horizontal and vertical prediction to capture the long-range geometrical pattern of the object for the global coherent predictions, even with occlusion and cluttered scenes. The basic idea of P2f Conversion is to find the coordinate system mapping between fisheye image and panorama image. That is to calculate the mapping position of each pixel on the fisheye image to the panorama image. The geometrical process of transforming a panoramic image into a fisheye image is shown in figure. The central idea of OSCOM is to conduct convolution operation of scenes in the spherical domain instead of the regular image domain from the preceding fish maps. It denotes the convolution kernel as a small patch tangent in the CFL surface where fisheye images are represented without distortions. We collect a high-quality fisheye dataset with sufficient number of images and the corresponding layout ground truth. The top view fisheye image dataset constructed by transforming panorama images counting the real fisheye dataset and synthetic fisheye dataset with a total size of 22,583. We show the layout estimation results by our distortion-aware convolution model on panel context F dataset. As shown in the figure, our results are almost the same as ground truth. In the same way, we also showed our deformed convolution results on Stanford 2D 3DF dataset and structured 3DF dataset, and both obtained objective results. Quantitative comparison for layout estimation between the proposed deformable convolution and other convolutions on the real dataset are summarized in panel context F. Stanford 2D 3DF dataset of table 1. It can be observed that OSCON achieved more satisfactory results than DCNV1 and DCNV2, which validates the effectiveness of our deformable convolutions for the facial image. We further verify the generalization of our method to room layout estimation. Our network is initially trained on the synthetic structured 3DF dataset. We then fine-tuned this model on the real dataset. It makes a remarkable improvement on the real datasets. We visually compare our layout estimation result by different convolution methods on panel context F and Stanford 2D 3DF dataset as shown in figure. Compared to DCNV1 and DCNV2, our network with OSCON can better handle the facial distortion caused by orthographic projection and produce high-quality layout results. Furthermore, qualitatively, our fine-tuned results with structured 3DF pre-training are significantly better than the results without pre-training, as shown in the last columns of figure. This indicates that the generalization capability and the efficiency of the proposed method. Table 2 demonstrates the performance of these four methods on layout corners estimation using panel context F, Stanford 2D 3DF, and structured 3DF dataset respectively. We considered CP 2DLU for the performance evaluation. The results display that our approach obtains state-of-the-art layout estimation from a single facial image on the 3 datasets. The qualitative comparisons of the four methods on 3 datasets are shown as follows. Our approach is superior to the other method on panel context F dataset and Stanford 2D 3DF dataset. Such as open corridors and severe occlusions. The qualitative comparison on structured 3DF dataset are shown in figure, where the scenarios are less complex than the two real datasets mentioned above. The results show that our approach can achieve more accurate estimation of localization of layout corners, especially for a better estimation of the cluttered scenes and open spaces such as the balcony and kitchen. Our method brings broad application prospectors in warehouse viewing and MR video surveillance. We display an MR-based real building video surveillance scene equipped with 9 fisheye lens cameras here in the recorded video. This is the ground image and the terrain existing 3D models. This is our video model. The top is our layout results. Next, can viewing area. Okay. That's all. Thank you for your attention.
Thank you, Min Min. for the next talk. So now we are moving on to the question and answer. So do we have any questions from the audience? So far? So, okay, so then let me start from me. Oh, wait a sec. Okay, so I think we have one question from Alex Bilo on Zoom chat. What's the advantage, disadvantage of orthoconv over simple convolution or deformable convolution? Have you tried orthoconv on non-fisheye images, and how does it perform on ImageNet, for instance?
Okay, do you mean the deform convolution on standard image?
For example, yes.
Yes, I made the experiment. The Stanford standard convolution on standard image, but not deform convolution on standard image.
And so your ortho convolution works better than the others in the conventional images, or do you have any comments on the advantages or disadvantages of your methods?
Excuse me, sorry,
could you have some comments on pro and cons about your ortho convolution?
Convolution.
Yes. Orthoconv.
Do you mean my contribution? Conclusion.
So your convolution strategy has some special, sampling strategies in it. And so what is the advantage and disadvantage of using this? What is good and what is bad?
Okay, I understand. The good is the layout estimation result is equal the ground truth. The ground truth in the corner position, such as the floor and the wall. Floor were the corner position of floor and the wall. I do the box shape room layout estimation with 4 corners. Yes.
Okay, I suppose it was the right answer to the question. And so maybe I have some questions. So for example, from the user's point of view, I think it's just easy to undistort all the images in advance and then run the conventional convolutions on it to detect the 4 corners of the floors. So would it make sense, or do you have any, more advantages to use your methods?
The other advantage is we use the LSTM network to capture the long range pattern to handle the complex thing with occlusion and clutters.
Okay. So I think we are just on time. So thanks again to Mimin. Thank you.
Thank you.
And so, okay, we finished all the presentations. Thank you for the attendees and all the presenters. Thanks again. And so please don't forget to go to the QA track A, which is QA track A in Gather Room to have additional questions directly to the authors. So you, don't hesitate to ask more questions to the authors. Okay, thank you again for all of the attendees here. And let's see you in the QA track A. Thank you.